he will talk about PDE on graphs and their continuation limits. Welcome.
Thank you very much. I'm really very happy to be here. As many speakers, first, or not speakers, participants, first conference, I wouldn't say after the pandemic, but, after a long while. And I have learned really a lot in this bootcamp about areas that I knew very little about previously. And I'll keep my talk also somehow rather basic. So I really want this to be somehow bootcamp and kind of clear, so that people from other areas who might be interested in this can still kind of get the gist and maybe get the idea about how some of the techniques work. So please, feel free to stop me. I don't have a kind of a big goal at the end to reach, and I'm, kind of happy to discuss this. So, okay, we said something about PDE on graphs. So these are motivated by graph learning. So what is kind of a typical setup, right? So typical setup is that one has a sample of some points, right, which in the space, right, and these may be samples of these digits from the MNIST data set that Jose Antonio was showing, right, or maybe some medical records and so on. It may be that these points lie in a very high dimensional space, right, but somehow if problems are genuinely intrinsically high dimensional, then they are typically statistically intractable. Usually there is some lower dimensional structure that we can exploit to make statistically reliable inferences. So the question is, how do we access that low dimensional structure? And somehow the viewpoint of graph-based learning is that we can create a graph out of these data points somehow to capture some of that geometric information. So what is happening is that one is connecting points, one is connecting nearby points, right? And I put too many points, right? But you have to choose a length scale, right? And then based on that length scale, you create your graph. And how to choose this length scale is, it's not, it's difficult in itself. But let's say that you were able to choose a reasonable length scale so that your graph on some level captures the geometry of the underlying measure from which the data are sampled, right? So, okay, so the object now that we have these vertices. So I have, xn is the set of vertices, x1 up to, well, okay, so maybe script xn up to xn. So these are vertices, and we have some weights. So wij is the edge weights. Okay, and then there are many somehow algorithms, right? So, I'll just write two which are, not in kind of entirely reasonable, right? But resemble those that are really used and are kind of going to be helpful for me in posing the analysis task. So, okay, maybe one of the tasks that one wants to do is clustering, right? So we would like to see if, so this is a typical problem in unsupervised learning. We want to see if there is some signal in the structure of the data itself, right? So what is a cluster? It's very hard to define axiomatically, right? But we would like to say these are somehow clumps in the data, right? We want to, if the data really all look like this, right? If this is my set of points, right? Then we would easily identify somehow two clusters, right? So these are all close by. There is a significant margin between them. If I have something like this, well, then you may say, okay, so here, here there may be a relatively dense region of points, and here there may be a relatively dense region of points, and okay, these points in between could be thought in some ways of some outliers, right? But the question is really, how do I now quantify this when I don't have really separated clusters and so on? And there are various energies that one can think of, and let's say the one that comes from spectral clustering would be the following. So we introduce an objective functional that acts on functions on this graph. So basically, I'll have a function u that will take this graph into real line. Okay, and if I, for this function u, let's say we write the energy as the sum of wij u at xi, which I'm going to write as ui,
minus uj. So this is basically just short for u of xi. Let's say squared, and okay, I put a sum here, and this is a double sum. So I goes from 1 to n, and j goes from 1 to n. Okay, so this is just what is a graph, an analgon of Dirichlet energy, right? So how can we use this for? And I'll just be looking at bi-clustering. So clustering, dividing into somehow two sets. So maybe what I would like to do is, okay, so if I want well, I noticed that for this energy, right, if I choose a constant function, right, so the smoothest function, right, so then the energy is going to be equal to 0, right? So, okay, then we would like to see, okay, what is the smoothest function which is orthogonal to a constant, right? So what if I minimize? So let's say, I don't know, u bar is argmin. Well, this is a convex problem, so it is the minimizer is unique, right? Well, sorry, it's not, right? When I add a constraint, then no longer, right? So let's say among all u's which are perpendicular, so to 1, so the dot product with 1 is equal to 0, and I minimize this energy. So E of u. Right. So now I'm having a function which has average 0, right? And is such that kind of its variation, right? The gradients measured in this quadratic norm should be as small as possible, right? So how will this function look like? Well, my guess is that what this function will do is, if I look at this function over, somehow I plot it in one dimension, right? So that on this cluster over here is going to be negative, then it's going to very quickly transition in this region here, because here there are very few connections in this graph, so there are very few weights. It is very cheap to transition here from this negative value to the positive value. And okay, let's say choose just two. You can. There are many minimizers, but let's say I normalize it so that it's normalized to have the L2 norm equal to 1, right? Then you hope to obtain a function like this. And let's say the clusters are the sets where u is positive or the set where u is negative. Okay, so yeah.
Just a quick question. Just to understand, the only way that x is appear in this is through the W?
Yeah, so indeed, right, I didn't define how my W is going to depend on x, but yes, right.
Because u's don't depend on x. U's don't depend on x.
That's right. Yes. Yeah, that's quite important remark, right? That the geometry, right, the way that the geometry comes in, right, when I created this graph is in this way W. And let me actually address this somehow right away. So there are two typical ways to define these graphs. So one is, a la random geometric graphs, which means that I'm going to choose some kernel function, let's say function eta, which, could be a constant function and then dropping down to 0. And we will set the weight, so Wij, to be just eta of the distance between the nodes xi and xj, right? So this is, if I choose this, then you exactly obtain a random geometric graph. So you connect things if they are within this length scale L, right? So this is like choosing this length scale. Whereas here, I still have a length scale, right? Which is kind of, the first moment of this eta, but it does so in a soft way, okay? And, very often one will take a Gaussian to prove some and make some statements kind of rigorous, right? It will be easier for me to take a compactly supported eta. So I'm going to look at eta, which is supported on the interval from 0 to 1. Another kind of typical construction is to look at the KNN graphs, which means that you just connect every node with k of its neighbors, right? Where instead of choosing, a length scale L, right? You choose the number of neighbors, right? Then the proofs, kind of the theoretical setup is similar to what I will be, saying. So everything can be done for those graphs. Of course, the models are somewhat different. The graphs that you obtain, look different. And for many things, KNN graphs are actually somewhat better in practice, but I will stick with kind of the graphs that I'll obtain over here. And I'll also say, okay, so to be able to explicitly state the length scale that I'm going to be using, right? I'm actually going to define, the typical modifier scaling. So let eta epsilon of z be equal to 1 over epsilon to the d, where, okay, I'll have a comment on that, but okay, eta of z over epsilon, right? So, okay, d, the dimension d that I should be using, if the data are on a manifold, then d should be the intrinsic dimension of the data. So you can say, well, wait, but I don't know what that is. Well, I do this more of as a mathematician because my minimizer, right, will be the same whether I have this epsilon to d or not, right? But I'm using such scaling where the limit as n and epsilon go to, as n goes to infinity and epsilon goes to 0, where I will be obtaining a reasonable limit, right? So, and also, while one can do everything when data really lie on a manifold, right? I'm going to mostly stick with kind of the data being somehow full dimension because it's just easier to write things. We don't have to use the notation, a lot of the language of differential geometry. Okay, so, right, so, somehow this is one model that I will be considering, right? So, energies like this, right? And minimizing such energies. Let me introduce another model, which I'm actually going to study first. And this other one is really fake, but again, this is just for pedagogical purposes to see somehow showcase some of the techniques that can then be applied to kind of more relevant problems. So imagine that instead of, so the second problem is, okay, so again, I have my points, right? And let's assume that there is a subset of points, right, on which I know what on which I have some information. So let's say, what is information? Maybe I want to somehow assign some label, right? So, I'm deciding, right, kind of what is the likelihood that this is an image of a cancerous lesion, right, versus that it is not. So I have some, if I'm in some regions, then I know what the answer is supposed to be. And now I would like to propagate that answer over somehow the geometry of these data, right? So let's say then my label, right? So this U would be given. So I know that this U over this set. So let's say there exists some set, capital U, over which I know that my function U should be equal to some function G. So over this set, U is given, right? So, in that sense, I would like to do the following, right? So I want to, I will be only looking at function U, which maps this script X, and without, those indices Xi, which lie in the set U. So those are not going to be free to assign. And I would like to minimize, so the task is to minimize, E of U subject to constraints that, well, actually, right, so I should, okay, maybe right, sorry. Let me write it like this. This maps U, this into R. So, okay, I look at a function which is free everywhere, but I add this as a constraint that U, restricted to those nodes, script X intersected U is going to be equal to G. So on some subset of my nodes, my function is given, right? And I would like to minimize this. And I would say, okay, if I, I would like to, highlight that, okay, if this is, if I use that W of I and J is equal to eta epsilon of Xi minus Xj. So this is the eta epsilon, these are the ways that I'll be using, right? So then it makes sense that I add indices epsilon and n to my energy, right? Because given a number of points, my energy is going to be taking a different shape. Okay, well, we know that, okay, so I'm not going to somehow quite do that, but, this is a, simple quadratic functional. I could do the first variation and write what is the Euler-Lagrange equation. And if I do that, right, what I will obtain, right, as the first of the condition is that, for every I, right, I'll have that the sum over J of, Wij of Ui minus Uj is going to be equal to 0. And this would be for every I, again, lying in this set, so xi does not lie in U, right? Not lying in U. Okay, well, this is what I will call the graph Laplacian, right? So I say, okay, maybe I change the pen. So L and epsilon of U evaluated, right? Okay, here I'm going to write explicitly xi, right? Would be, the sum over j of eta epsilon of xi minus xj U at xi, which I denoted by ui minus uj. Okay, so in this case, right, and I have the constraint again that, U restricted to the set U, okay, is going to be equal to G. Again, this is U. Okay, so I have these two prototypical problems, right? So let's say this is, the first problem here is this variational problem, and the second problem is, something that looks like an elliptic equation on a graph.
Were there in your difference of views?
No. This is just when I do the first variation, right? Then I obtain the graph Laplacian, right? And right, my equation, I didn't write the first order condition, right? That this guy is going to be equal to 0. Thanks. Okay. So now the question is, right? If we are having a reasonable statistical procedure, right, then it should be the case that if my data are really sampled out of some manifold or some measure on a manifold, right? So in this case, right now, what I will be assuming, right, is that there exists an underlying manifold, or which, the geometric aspect in kind of in this talk will be restricted to saying, right, that there exists a set omega in R to the D, so it will be a full dimension. Again, everything can be done on manifolds, it's just more complicated to write down. There exists a set of full dimension such that all of these points here, xi, are random samples of a measure mu, and omega is describing the support of this measure mu. Okay, and the kind of the assumption that we need, right, for our theorems, which is not entirely reasonable, right, but it kind of is a first step, is that this measure mu is absolutely continuous with respect to Lebesgue measure, which would be then, it's absolutely continuous with respect to volume form on a manifold, and this rho has the property that it's bounded above and below by positive constants, right? So C1, which is positive, and C2. Again, this second one could be removed, but this first one is kind of difficult to remove in the setting here. So we assume that kind of our measure does not degenerate on its support. And now the question is, if I'm drawing a different sample, or perhaps I draw more and more points, is my statistical procedure going to be stable, right? Am I going to be obtaining somehow similar answers? So this is this continuum limit. This is the consistency question for on the level of these, in this case, quadratic variational problem, in this case, a linear equation, right? But one could ask with these, the second technique that I'll ask, one can treat actually also non-linear and non-convex problems in terms of kind of finding the minima and deciding whether the procedure, because the minimum is the answer to our procedure. So again, the main question that I would like to address is that whether as n goes to infinity, these procedures converge, and to identify what do they converge to, and maybe discuss somehow more or less the general setup of that. Okay, so that's kind of the the topic of this talk. Right. Okay, so before I kind of move on, right? So I just recall, how do we, connect what is happening in a discrete point cloud, right? So random discrete point cloud, and what would be happening in a continuum, right? So there will be, you know, kind of 3 levels that I'll do that, right? So first I'm going to look at a fixed smooth function, right? I'm going to plug in that smooth function into this Laplacian, into the graph Laplacian, and see how much it resembles Laplacian on this underlying set. The second thing would be what happens at the level of the solutions of a PDE, right? Because you know, I don't know the solution of the graph PDE. I don't, you know, how exactly it relates to solution. Then it's the function is different, and I would like to obtain estimates on the difference of these 2 functions. And the third thing would be what happens if I look at minimizers of variational problems. Okay, so for the first task, when I'm looking at the fixed function, right, this is somehow pretty classical, right? You know, we are looking at the empirical estimate on some sum related to that function. It's more or less like a Monte Carlo integral. But okay, let me somehow write down how that is done. And you know, one of the tools that we need for that are concentration inequalities, right? Of course, that's a big field in itself. There are various concentration inequalities adapted to different situations. I'm just going to recall one, you know, perhaps one of the oldest ones, and you know, apply it on one of the problems over here. And again, just scratch the surface of that very big field, right? So, you know, let's look at Bernstein inequality. So let's say, assume that, so this is all in R. So, you know, we have x1 to xn are, you know, random variables with values in R, right? So variables. So I, the random variables. This is not a good idea. Okay, we have that they have finite expectation, right? So, and for mean, right? And they have, they're also bounded, you know, something like L infinity, right? So their distance to expectation is less or equal than some finite number B. And let's say V is the variance, right? So this is the expectation of xi minus m squared, right? In that case, let me look at Sn, which is the, you know, just the sum of these variables. So x1 plus n, right? Then what we have is that the probability that the average of this sum deviates from mean by more than positive number t is less or equal than e to the minus n t squared divided by 2 times variance plus, okay, I'm, you know, here not putting the optimal constants because I don't need them, but I get something like this. So first of all, so I you know, what do you expect, let's say, from law of large numbers, right? You expect that, you know, the typical distance of, you know, the average of the average to the mean is going to be like square root of n. And indeed, you could see that, you know, if, you know, p is, you know, less than some constant times 1 over square root of n, right? Then you exactly get here, you know, 1 over n times n, right? So this can only be small, right? If t is less than some constant times 1 over square root of. So you see that it's exactly that length scale, or, you know, in terms of n, right? From law of large numbers, when this probability can be expected to be significantly less than 1, right? And then, okay, if I have that p is a lot less than 1 over square root of n, then I can expect that this probability is going to be very, very small, right? So here we are, of course, interested in, you know, I want to make sure that something happens with high probabilities. We would indeed be interested in those regimes where this can be made as small as I like, you know, let's say less than 1 over n to the 4th or something of that flavor.
Is V the sum of the expectations?
V is the variance.
So it's the same variance. I mean, I think
The
the
max.
sum is, huh?
No, they are all IID, right? So I just wrote I because,
Oh,
right. Yeah, this is a simple form of, of course they're right. Okay, well, then let's look at this graph Laplacian. So let me create some space. So, right, well, instead of, writing it like this, okay, let me go back to writing as u of xi minus u of xj. And, okay, so here I just use this as a definition for the Laplacian, right? But okay, now, as soon as I wrote it, right, I'm gonna change it a little bit because I'm interested in kind of limits. Again, all right, so I didn't really quite explain, right? But as n goes to infinity, so I get more and more points, right? It is natural to take epsilon to go to 0 for various reasons. So epsilon came out of necessity, right? Because we needed to connect the nearby points to recover the geometry. If I have more and more points, I can, recover the geometry at a higher resolution, and I don't want to connect points which are too far. So epsilon should scale in some way with n. Okay, that's one thing. So epsilon you should think as going to 0 as n goes to infinity, and n goes to infinity because that's the problem that I set out to study. What happens if I get more and more data points? Okay, so since I want to take those limits, I want to scale things in such a way that they will make sense in that limit. So I'm going to divide this by 1 over n epsilon squared. And I'm actually going to, there is also one constant of proportionality that depends on the kernel eta, which I'm going to call sigma eta. And I'm also only going to specify it later. But again, this is just a positive real number, which depends on eta. So given this, right, well, I noticed that this seems to be somehow an empirical, somehow average over a certain function. And what would that function be? So, or operator be? So this would be, if I have a function u, which is defined everywhere on omega, right, then L epsilon of u would be 1 over sigma eta epsilon squared times the integral of eta epsilon of y minus x u of y minus u of x. And okay, I have that the density of mu is rho, so rho of x, rho of y dy. Okay, so you could see, right away from the definition, right, that the mean of ln epsilon for any n is nothing else but L epsilon of u. So given a function u, if I take a fixed function u, right, then this is nothing else but the mean. And let's see somehow what is so the way that I will connect the graph Laplacian to the ordinary Laplacian is going to be in 2 stages. So first I get rid of just the randomness, but not of the length scale epsilon, right? So first I'm going to connect this with an integral operator that still has the length scale epsilon. And then in the next stage, I'm going to connect this non-local integral operator with the actual Laplacian, right? Okay, so, if we define, you define, variables yj to be, well, okay, let's forget about sigma for a second, right? But I just define this to be eta of xj xi. So in this case, I is fixed. And if I apply the Bernstein inequality, and I don't have quite. It's satisfactory really to go through the numbers, but I feel that I don't quite have time to do that. But you just apply. Well, okay. Let me just do a little bit of that, right? So this eta epsilon. So what is the maximum of so the mean of this is going to be sigma eta times L epsilon of u. But let's say what is the size of this going to be bounded by? And let's say I'm taking a function u, which is a smooth function, right? So then the size of this is going to be bounded by, well, eta is of size 1, but then you divide it by epsilon to the d. So this is going to be 1 over epsilon to the d plus 2, right? But then here, okay, this is like a gradient, right? So this is going to be bounded then by Lipschitz constant in u. When multiplied, how far can these 2 points be within the support of eta epsilon? Well, support of eta, right, is of size 1. When I rescale it, it's of size epsilon. So I get 1 epsilon over here. And okay, then, the right thing to do is just to adjust over there. And you do the similar exercise for variance. And what you basically obtain is that the difference, so you apply by Bernstein. Is going to tell you that L and epsilon of u minus L epsilon of u is going to be less or equal than lambda over 2 Lipschitz constant of u with probability 1 minus e to the, so minus a small constant and epsilon to the d plus 2 lambda squared. Okay, and they are kind of now variants of this in a sense that, okay, I just did it for 1 point. If I want to do it for all points at the same time, right, then you could use something like a union bound. So you may obtain something like ln of n, or I think in that estimate that the polling is 3 times ln of n. And then also, if you want to have this also somehow for every point on the set omega, even those points which are not somehow sample points, but you still would evaluate the graph Laplacian, right, then you would need some partitioning somehow estimate. So you may have to pay a little bit of price over there, right? So if I want to do this uniformly against over sample and also allow for to go out of sample, then okay, I need to pay a little bit of price. But now, okay, this may seem like a kind of an odd way to somehow pose this, but I want to look at 2 things. So epsilon is going to be small, and I have 2 options. So first, just to see when can I make this small. So, okay, so the boundary of the region when things are small is when lambda is of size 1, right? So I notice, to interpret this, if lambda is of size 1, right, then for this to be small, I need that epsilon is much bigger than 1 over n to the power d plus 2. And again, I'm not writing logarithms. Let's say I'm neglecting maybe some logarithms, but I'm really just looking at some algebraic scalings, right? So again, if I allow myself, I just want, I'm at the boundary when I have any approximations, which is when lambda is 1, that will hold if epsilon is bigger than n to, well, no, this is not like this, right? So this is 1 over d plus 2, right? And the other is when I have a linear approximation. So I'm going to take lambda to be equal to epsilon. So in that case, I'm going to, right? So, right, you see here we have epsilon to the power d plus 4, right? So I want, then I'm going to have this with high probability if epsilon is much bigger than 1 over n to 1 over d plus 4. Okay. And again, I'm neglecting logarithms because I need some logarithms so that I get their powers of n in the probability.
Could you say one more time what lambda is?
Oh, lambda is a number that I choose, right? So I'm choosing how accurate of an approximation I want, right? So, the first thing is that I'm going to have any approximation. I need lambda to be small, So I'm really choosing lambda at the boundary of that region, right? So basically, if epsilon is not bigger than this, you're not going to have anything, right? Then you have too much randomness, right? On the other hand, if I want to have linear estimates, so now I'm going to be interested in kind of obtaining quantitative estimates, I'm going to be working in regimes that look like this, right? So this is kind of very basic as to how many points do we need per neighborhood so that we can get some reliable somehow estimates. Okay, and the second, the second thing is, now the second step is, so this would be, from random to non-local, right? So this estimate is from random to non-local, right? So it should be. And okay, now let's look at the other estimate, which would be non-local to local or differential. So let me consider, if I like a lemma, right? So let U be a C3 function on omega, and let's consider a point, x such that distance from x to boundary of omega is bigger than epsilon, right? So I do not want my non-local operator to go outside. In that case, we have that this non-local guy. So L epsilon of U minus. So note that, right, these operators, right, this guy here, right, is a positive semi-definite. So I'm really looking at the negative Laplacian, right? So then we're going to have plus 1 over rho divergence of rho squared gradient of U is going to be less or equal than C times some constant, right, times C3 norm of U multiplied by epsilon, right? And this is obtained, okay, so I'm not going to go through this. It's also a very enjoyable, actually, exercise. You do Taylor expansion on this, right? And I just want to note that, right, there is going to be a cancellation, right, somehow in the first term. So maybe just to observe that, when I integrate, eta epsilon of x minus y times gradient U of x, and now, okay, this is dotted with x minus y, and let's say, you'll have also expansion in this term, so rho of x plus, gradient rho at x dotted with y minus x plus higher order terms. I'm not writing the full thing out. I'm just, because I need the second order term. I just want to point out, the only thing that I'm pointing out is that, okay, this term will give me something, so I'm going to forget about it for now, right? And I integrate against dy. Note that eta is an even function, so I may not have mentioned, well, I kind of did because I defined everything in kind of as a radial kernel. So I should really then write it like that. But note that this is an odd function and this term drops out. So we'll only obtain the terms that have either second derivatives of U or have gradient of rho. And those two terms survive. And you recover your operator in the end and you recognize that it's this operator over here. Okay. So again, that's purely somehow a calculus exercise. There is nothing to it, but it's still enjoyable to do it to see exactly the operator that pops out. Okay, so in conclusion, right? So I don't know. This is maybe this is lemma 1, and then this ought to be lemma 2. So okay, let's say something. When you combine these two things, you have that with high probability. So under the conditions on epsilon, right? So under the conditions on epsilon, if function U is C3, then with high probability, we have the following. So, okay, let's say, if epsilon is much bigger than 1 over n to 1 over d plus 4, and U is a C3 function, then with high probability, we have that L n epsilon of u. We have that maximum over I going from 1 to n of this guy here, right? Evaluated xi minus the operator over there at xi is going to be less than some of these two terms. So I have C3 norm times epsilon, right? And then I have something like this. So altogether, this is less than some constant times u in C3 multiplied by, well, okay, here I took lambda, this is the case. I'm just writing one statement for lambda being equal to epsilon. So then here I'm just going to have epsilon. Okay, so this is what we know about our operator. And then, well, let's see, how can we do this to obtain the information as to how far is the solution. Okay, now the equation comes back on. So I set this equal to 0. How close is this to connect to a solution of a differential of a PDE? So now that I have this consistency estimate basically between my discrete operator and the continuum operator, right? Then this is kind of pretty standard. We just need to use some stability. Let's say for these elliptic equations, we have the comparison principle that can provide somehow the desired stability in L infinity norm, right? So yeah.
The operator you get at the end, is that supposed to be self-adjoint with respect to L2?
Yeah, right.
I guess I'm just having a little bit of trouble seeing why there's a rho squared inside the divergence.
Yeah, so okay, so on one hand, that would come out of the right. So on one hand, that would come out of the expansion, right? On the other hand is we obtained this guy as right. So we obtained this guy as the first variation of the graph Dirichlet energy, right? And the graph Dirichlet energy is a double sum, and each of these sums has one row in it, right? So this is where two rows somehow, you can see it on the level of that variational function of that. Due to the fact that it's double sum, it would be quadratic with respect to density. And then, okay, here it's kind of a little bit hard to see on this level, but then on the level of, that's why I was saying that Taylor is kind of satisfactory because it exactly gives the right power over there. So yeah. Right. So okay, maybe I don't need Bernstein anymore, right? So let me write here, this fact from PDEs. Okay, so imagine that I'm actually solving a PDE on domain omega, right? And that, I say let gamma be the boundary of omega, and let's say assume that this omega has the regular enough boundary so that the standard existence uniqueness theory works, right? So I note that, okay, well, let me look at, kind of a linear elliptic, L is elliptic operator. So for example, let's say LU is negative 1 over rho divergence of rho squared gradient U. Note that I'm not, most of PD people would not put a minus sign, but in viscosity community, this would be quite welcome. And right, then I'm looking at the equation. So, okay, I'm looking at the equation LU is equal to F, let's say in omega, and U is equal to G on the boundary of omega. So this is my problem P. Then I would say that some other function, let's say V, is a super solution of P, of the problem P, if we have that LV is bigger or equal than F in omega, and that V is bigger or equal than, so I have both, that V is bigger or equal than G on the boundary of omega, right? And we have analogous notion of a sub-solution. If we just reverse these inequalities, right? And then kind of the, standard theory that, the standard theorem, right, that you learn in PDE 1, on which the theory of viscosity solution eventually is based, right, is that if, okay, let's say W is a sub-solution and V is a super solution, then we have that W of X is less or equal than V of X for all X in omega. Right, so note that, right, what does the, the information from the definition tells you? It just tells you that V must be bigger than U, I mean, G is between them on the boundary. And that inside, right, they have some operator estimates, but it doesn't tell you anything about how the values of V and W are related, right? The comparison principle tells you that then V must be less or equal than, greater or equal than W everywhere, somewhere in domain. And okay, note that this implies, so this immediately implies, because U is a solution, so therefore both a sub-solution and a super solution, so you immediately get that any solution, right, has to lie between these two extremes, okay? And I know that if I look at the graph problem, because the operator on a graph is also positive semi-definite, you have the comparison principle for the problem on a graph, so the analogous, definition and theorem also holds on the graph, okay? So, okay, so what is then the problem that I'd like to study? Okay, so that I don't have to deal with Neumann boundary conditions, I'm gonna, create a super fake problem, right? Which is somehow the following, right? Is that imagine that, okay, so we have our domain omega, right, as usual, right? And now, okay, let's say that I was able to identify, right, the boundary region for omega, right? So I call this, gamma epsilon. So let gamma epsilon be the set of those points such that the distance from X to boundary of omega is less than epsilon, right? And okay, so I'm going to be considering the continuum problem is just this, right? So it's just that minus, okay, I don't need 1 over rho, but I'm just writing the functional rho squared gradient U is equal to 0 in omega, and that U is equal to G on the boundary of omega. And I also have the graph problem. So if you like P and epsilon, which says that L and epsilon, at xi is equal to 0 for all xi lying in omega without G epsilon. And I have that U, if you like, and right here, and epsilon of xi is equal to G at xi for all xi lying in gamma epsilon, right? Okay, and so if we have this, then okay, we can write the following, right? So Yeah, let me write somehow the full statement. So let's consider lambda to be less or equal than 1. Then we have that the maximum over, all xi lying in, well, over all of the xi's in the sample, u and epsilon of xi minus u of xi, where u is now the solution of the equation, right? So this is very different than the setting that we had for the pointwise estimate, right? Because I have two distinct problems. I solve each of them separately, and now I compare the two, right? So this is going to be less or equal than the c times u in C3 multiplied by lambda plus epsilon, and this holds with probability 1 minus some little constant c exponent negative another constant n epsilon to d plus 2 lambda squared plus something of the flavor. So again, right, we need again, if I want lambda to be of size epsilon, right, or equal to epsilon, then I need epsilon to be much bigger than 1 over n raised to the power d plus 4. Okay. Now, how do we prove this using the comparison principle? Okay, so on the level of the continuum PD, I know how to create super solution that will stay a little bit above the actual solution, okay? And then I will show that I could use those continuum super solutions to create discrete super solutions. So if I downsample the continuum super solution to the discrete space, then these estimates, right, will be enough. These estimates will tell me how much of the super I need in order to have a discrete super solution. And then I will know that my discrete solution is between somehow the two. Okay, so that's basically the whole recipe. And okay, let's just somehow carry it out. So let's say I need a barrier function. So let phi be the solution of the following. So, okay, I'm going to call, okay, I call this operator delta rho, right? So let's solve a negative delta rho of phi is equal to 1 in omega, and phi is equal to 0 on the boundary of omega. Now, it's easy to show that the minimum of phi has to be reached on the boundary, and therefore phi is positive in omega. Okay, and right, and then okay, so I know that if I consider this, but here is my the function that I'm going to be looking at. So I look at u plus delta times phi, and then I add plus some epsilon times the Lipschitz constant of g. So let's assume that g, the boundary data, are Lipschitz continuous, right? So what is that I do here, right? So I create a little bit of a super solution, and I lift the data to account for the fact that the boundary data are not assigned exactly on the same set, right? So here it's just on the boundary, whereas here is in this thickened layer. So I want to kind of make sure that I stay above that. And note that the maximum, so the maximum that g can deviate away from the boundary is, exactly by somehow this amount. So it should be enough to have a super solution. So note that this guy solves the equation, if I call this, I don't know, I just call it u delta. Note that then what we have is that rho of u delta is equal to delta in omega, and that okay, if you like, u plus delta phi, right, is equal to g on omega. Okay, so on boundary of omega, and it didn't really write this as a solution of a problem because, you know, here I just lifted this even more somehow on the boundary. So I feel like I just remember these two facts somehow as separate facts, right? And okay, now I want to show that this, when I restrict it to the discrete set, is going to be a super solution. So what we have is that L epsilon n of, okay, I write the whole thing. So U plus delta phi plus epsilon times the Lipschitz constant of G. Well, okay, this is just a constant, right? So I don't really need it when it doesn't make any difference whether it's there or not when evaluating the graph Laplacian, right? So, okay, what do we get here? So I get, you know, minus rho delta of, right? So, okay, I know that this guy, right? This guy is precisely this guy here applied to U plus delta phi, right? So it should be this applied to U plus delta phi. So I get, you know, this applied to U plus delta phi. Right, and what is the worst that can happen, right? So at worst, I'm going to have an error like that. So minus, okay, now I have to say, I stated this only for lambda being equal to epsilon. Let me try to recover there. So I'm going to have, you know, C times, okay, U in C3 plus actually phi in C3, if you like, plus 1, and then epsilon plus lambda, right? But I know that this, you know, C3 norm of phi, this is just some constant that depends on the domain, right? So instead of, you know, having a constant phi here, I'm just gonna note that I still have this statement with perhaps a different domain dependent constant. Okay, and right, I would like, yeah. So, you know, what do I get here? U is a solution of this problem, right? So there I get 0. And phi is a solution of this problem. So I get precisely delta. So I get delta minus C omega U C3 plus 1 epsilon plus lambda. So this is going to be a discrete super solution as long as my delta is big enough, right? So I'm basically discovering how big delta needs to be. So if delta is bigger than C omega, okay, U C3 plus 1 epsilon plus lambda. And okay, one also checks on the boundary that you know, this U right, U delta, you know, on gamma epsilon is bigger or equal than G. So this is a discrete super solution, right? Okay, so that so this means, right, by a discrete kind of comparison principle, what I have is that, okay, I don't want to go too low because I know that then it's not visible. Right, so what we have is that U delta, right, is bigger or equal than U and epsilon, because again, this is a super solution and this is a sub solution, right? And you do the same trick, right? So on the other side, so here we have U minus delta times phi minus, right, with a minus, you know, epsilon times the Lipschitz constant of G, right? Okay, so right, phi is a smooth function, so it is bounded, right? So basically what we have is that, you know, the difference between the upper and the lower bound is less than, you know, some constant times delta plus epsilon, right? So what we have, oh, and by the way, note that U lies also between those two, right? Because I have created them by increasing U. So basically what I have is that U and epsilon minus U, again, the maximum as it is written in the theorem, right, is bounded by what we have is 2 delta, well, let me write it like this. So 2 delta maximum, or, you know, I in L infinity plus 2 epsilon times the Lipschitz constant of G. But then what is the delta that we needed, right? So the only condition on delta that I had was this thing over here. So let me take the smallest delta that is allowed, right? So then I get that this is less or equal than, so again, I get some constant. So, okay, again, U is the solution. So this is again just some constant. So I get some big constant multiplying epsilon plus lambda, which is what we want. Oh, okay, so there I wrote it a little bit different. I mean, in the end, this is not so important. But I just want is, so okay, if you now choose lambda to be epsilon, right, then you obtain a linear estimate, right? Again, for epsilon scaling, right? So what is important is that this works somehow for this scaling over here. Right? Okay, so this, right. So this, I'm not going to get to the variational part of our talk, right? So, you know, we can discuss this. This is not actually, right, this you can find, let's say, in Jeff Caldeir's calculus of variations notes in a very similar form to what I presented. So, you know, I just wanted to kind of in general show, right, how, you know, the standard PDE techniques can be used in this random setting. The other side would be, how can the techniques from calculus of variations also be used in this standard setting, right? So there is this, so these PDE techniques, they give you quantitative estimates, but if you're just interested in whether minimizers converge to minimizers, then there is this notion from calculus of variations called gamma convergence, which is appropriate here. And I'll just mention one thing. So there you do not get quantitative estimates just from gamma convergence, but the advantage that you get is that those variational techniques work basically in the setting. Okay, again, I'm neglecting logarithms, so 1 or n to 1 over d. And that is actually quite nice. You know, you can get that, you know, solutions to equations like this actually converge without having pointwise consistency, right? So, you know, we show that even for if you take a smooth function, you need it at least, you know, epsilon to be bigger than 1 over n to 1 over d plus 2 to have any estimate, right? Yet for variational techniques, because, you know, for this PDE, I can write down a variational formulation, right, as a minimizer. Those variational techniques go down all the way to here. And for most of the problems, right, let me just say that this is really kind of a hard bound. Okay, logarithms can be discussed, but this bound here is kind of hard because that is the typical distance between neighboring points. If you take epsilon less than that, most of the points will not have any neighbors within this, and you're not recovering any of the geometry. So going below this is ridiculous, right? You know, then you're not having any geometry in your graph. Again, okay, you know, here I'm neglecting logarithms, then, you know, what does this much bigger means, right? But I would say in terms of scaling, this is kind of the hard bound. So somehow these variational techniques go all the way to this kind of hard bound. Okay, so that's all that I'm going to do today. Thanks.
Any questions?
I guess at the start you assumed the lower bound on your density. So at first I thought this was more like a sampling thing, like you want to combine enough points to cover an sample. But actually, like the bigger problem is more like branching density of your operators. Is that?
Yeah, I mean, if the density is 0, then the typical distance in my sample may be bigger than this length scale, right? So I would need to adjust this length scale, right, so that I still have something. So it may be, you know, that, right, if you know, I don't know, you have some algebraic decay and I choose some different scaling over here, then my graph will still recover the geometry based on your sparse data. So that is possible. So it's not, you know, yeah, it's not kind of that it is fundamentally kind of not working, but one needs to work with length scales which are then adapted to the fact that you have very sparse regions.
Do you also need the lower bound for like the stability of the PDE?
Well, you know, if my PDE, right, so if my graph is disconnected and so on, right, then I will not have uniqueness and so on, right? So I see a lot of problems, right, if the graph is not connected. So yeah, I would say yes, right.
I really like this barrier function approach, but in this simple linear setting, wouldn't it have been easier to sort of just look at the difference of the graph and the continuum function and then see that it solves the graph Poisson equation, and then use some boundedness for that equation?
Well, I would say that's kind of similar, right, kind of thinking, right? Because, right.
There's no particular reason that you use the barrier approach here. Or is it to incorporate the boundary conditions in an easier fashion?
Yeah, I don't know. It's kind of hard for me to say. This kind of was the first thing I thought of. So right.
So here you went straight up to actually show the convergence of your first order conditions to something, and what does the energy converge to? Like, I mean, what is the limit? So you start with the discrete problem and you say, let's go to the continuum, but like, what is it that I'm solving actually in the first place? Like, let's say I'm sampling, like, is there like some energy that makes sense that I'm actually minimizing in the first place?
Yeah. So the n epsilon level, right? So this would be, precisely, then double sum, okay, and then 1/2, right? So, okay, eta epsilon of its I. Yeah. I mean, okay, ui minus uj squared in a continuum energy would be just the integral of rho squared gradient of u squared dx. And okay, now what is the relationship, right? So that would be this gamma convergence. So basically, as n goes to infinity and epsilon stays above. Okay, now I'm making this precise. So ln of n over n to power 1 over d, d is bigger or equal than 2, right? Then this e and epsilon gamma converges. Okay, I didn't say the full thing to e in this TLP topology, right? Because the problem is that naturally, right, these functionals are posed on different spaces, right? So this is posed on a discrete space, and this is posed on a continuum space, right? And kind of for gamma convergence, you need all of them to live in one metric space. I mean, that's kind of the standard setting. And this can be done by looking at your metric space. So your metric space, I don't know, let Y be the set of pairs where the first component is a measure and the second component is a function. So where F lies in L2 with respect to nu. So you have this big space, right, which contains both the discrete setting where this would be a discrete measure and the continuum setting where this would be a continuum measure. So you need to put the right metric on the space, and then you can recover the gamma convergence.
Okay,
right.
so before talking about how, let me ask you why. I mean, actually, I recovered the same thing, and I thought I made a calculation error with this term square. Like, why does it make sense to minimize this? So you said, okay, so I understand in the discrete case that's what people do, but like, why should I have not a row in there? Like, I mean, it sounds.
Yeah. So okay, here is my kind of point of view on all of this, right? I feel that we should do all of the modeling in a continuum setting, right? And then on the graph, you just see what is the appropriate discretization of what you want here. So somehow on the continuum, right, is the right way, because that says, if I have the full information, this would be my decision, right? And there ought to be some statistical reasons, right? So when I look at the spectral guide here, right, so this is telling me that it's cheaper to cut in sparse regions. Maybe that's statistically good, maybe it isn't, right? It's for someone to analyze and decide. But basically, on this level, you can make sense of what does it mean? How does the geometry of the data, right, which I can measure, I don't know, in some way, in a way that needs to be defined, right? How does the geometry of the data, relate to what is the product of the procedure based on this functional versus some other and so on, right? And let's say, Nicholas and Franca and Baumgart, right, they have their paper where they look at, how does the spectral clustering relate to the geometry of data. On some, this is all at a very rudimentary level. I'm actually surprised that there aren't more studies of this precise question.
Yeah, because this would give you you started by saying there's no axiomatic definition of a cluster. Well, I mean, that's pretty axiomatic, right? It's like this is a cluster.
Yeah. Here you chose your model, right? Yeah.
There's a bit out of time, so we could reserve the question for the speaker in the break. So let's thank the speaker again.